All right, we are now getting into some of the really cool stuff of Spring Framework 5. We are going to start looking at reactive programming. Now, you may not have even heard of reactive programming or may not have any idea what reactive programming is. Don't worry, we're going to start off talking about just what is this whole thing called reactive programming and why it's such a big deal and some of the common terminologies and how it's been implemented. So reactive programming's been around for a little bit. It's actually some very old concepts, but now we're seeing some new modern programming paradigms come into play that makes it more appealable. So you can do some pretty interesting stuff with it. The first few videos in this section are going to just be informational about reactive programming, and then we're going to start getting into actually setting up a reactive web application using MongoDB. All right, in this video we want to talk about the Reactive Manifesto. So this was originally published in 2013, and you can go over to www.reactivemanifesto.org to read it in its complete form. Some interesting authors there. You have Jonas Bonner. He's the co-founder. Ka's a pretty cool library focused on a lot of big-scale distributed type systems. Dave Farley, Roland Cohen, and Martin Thompson. I want to point out that the term reactive is really getting overloaded in the IT community. There's a lot of disinformation out there, I guess you could say. A lot of confusion about what is and what isn't reactive. It's kind of becoming a real buzzword right now. So there's several reactive paradigms out there that we need to clarify. So in this presentation, I'm referring to reactive systems, and this is a architecture and design pattern. And you'll see like cloud native and cloud-based applications. So that type of systems, I think the large scale self-healing systems like Google's Gmail is a great example, or Amazon.com, obviously a reactive system. They do not go down on Black Friday sales events. And then reactive programming is much more granular. It's focusing on event-based. It's asynchronous, non-blocking programming techniques focused on handling an event, and that event would probably be within a reactive system. So a reactive system is a much more broader concept. We're looking at how you're laying out your servers and your microservices, whether or not you're using messaging or big monolithic application. So it's more at an architecture level, while reactive programming is the technique that you're using to code in. Now, functional reactive programming is also a buzzword. You're hearing a lot of functional buzz right now, especially in the Java community on the heels of Java 8. The founders, one of the founders of the Reactive Manifesto, believes that functional reactive programming is definitely misused right now by a lot of libraries that are claiming to be functional reactive programming libraries, when in fact they're more reactive programming. I'm not going to get into the nuts and bolts of that. Just want to make you aware that there is disparity in the community about what is functional reactive programming and reactive programming. So some people believe if you go functional model and doing reactive, you're now doing FRP, but not necessarily the case. So let's take a look at the Reactive Manifesto. This is going to be looking at 4 areas, and this is an image adopted right off their website: responsive, resilient, message-driven, and elastic. So let's take a little closer look to what each one of those means. So responsive, it means that the system is going to respond in a timely manner. And responsiveness is the cornerstone of usability and utility. And I'm not sure if everybody understands what cornerstone means. A lot of times when you're building an old building or an old architectural style, is you'd set down a cornerstone, which became the stone that you built upon the entire building. So that's what that connotation means in a broader sense. So that might get lost in other communities outside the US and Europe. Responsiveness also means that problems may be detected quickly and dealt with effectively. So this means that the system is going to effectively be self-healing. So responsive systems also provide rapid and consistent response times. And this consistent behavior simplifies error handling and builds end user confidence and encourages further interaction. So think about if you're using like Facebook and you're on Facebook and Usually Facebook works pretty consistent for me, but there's times when it's slow and I get frustrated with that. And it's usually when I'm on my mobile and have a bad data connection. So having a consistent response is important for your end users. So resilient. So system stays responsive in the face of failure. So resilience is achieved by replication, containment, isolation, and delegation. And then failures are contained within a component. So you don't want a single part of the system failing and taking down the whole system. So recovery is delegated to another. That means there's a redundancy in the system. So there's no single point of failure in the system. And then high availability ensured by replication where necessary. So this be like if you're running a RabbitMQ server, you'd be running in a cluster so that one of the nodes in the cluster could go down. Or if you have microservices, you're going to be load balanced against multiple nodes of that microservice. And then elastic. So the system stays responsive under varying workload. So reactive systems can react to changes to the input rate by increasing or decreasing resources allocated to those service inputs. And they achieve elasticity on cost-effective platforms, so using commodity hardware and software. And Amazon.com is a great example of this because they do run a lot of nodes behind Amazon.com, but both Amazon and Google are well known for using commodity hardware, so just the cheapest servers that they can find. And they structure their system so that that cheap little server can go down and it doesn't matter because they have other things to back it up. And then also, like Google is the founder of Kubernetes, and within Kubernetes, you can look at a workload and say, okay, well, I want 3 nodes of this running, but if it starts getting busy, if the CPU goes above X, bring on additional nodes to handle the load. So it will automatically scale in response to the load. And when that load goes away, then it'll scale down as well. So having this dynamic scaling is important. And while it's doing this, the system will stay responsive. So for the end user, the user experience is the same depending on if there's 5 users, 5,000, 50,000. The experience for each user is going to be the same in this. Now, this is probably one of the more important parts for us as far as being Java developers. Reactive systems are message driven. We rely on asynchronous message passing to establish a boundary between components. So this is going to ensure loose coupling, isolation, and location transparency. So message passing also enables load management, elasticity, and flow control. So this makes it important because now you have a distributed system and you're passing messages between it. So if you're sending a message, and just for clarity, a message can be going over like RabbitMQ, JMS brokers such as ActiveMQ, can even be a web service call because you are posting the contents of a message to a REST endpoint. So the message passing can take a number of different forms, but the concept remains the same, is that you're passing some chunk of data, whether it's JSON, XML, a serialized object, you're passing that message across some boundary to another system that's going to act on it. And location transparent messaging means that you're not dependent on server A talking to server B. You're going from a message group, a cluster of microservices A to a cluster of microservices B, that you're not concerned about the specific server. So this is an important architecture shift. And then the non-blocking communication allows recipients to consume only resources while active. And then this is also important. So if you have, say, a message queue, you can have a consumer come up. You could have 1 consumer, 5 consumers. So you can dynamically take that. And the consumers, they're not active, aren't going to be adding it to the overall system load. Now, I stole this diagram right from the J Hipster guys because I think it's really good. We hear the term cloud native. The Spring guys definitely like to talk about cloud native. And this is a good overview of what that involves. Netflix has been a huge contributor to the components within Spring Cloud, so there's a lot of cool stuff there. And what we have is a distributed architecture, probably going to be deployed in Docker containers. There's a number of different ways of managing those containers. Kubernetes is one that I mentioned. Docker Swarm is another. There's Apache, I think, is Mesos. So that there's a number of different ways of managing this. And then there's different ways of like using like Zool and Areca. You can just pull up these nodes and you could manually do it with these. So now you have a truly distributed application here. So if you're not familiar with the Spring microservices, what's going to happen here is if I deploy a microservice, it's going to wake up, go out to what you see on the diagram as the JHipster registry, and get its configuration from Spring Cloud Config, and then register itself with the Eureka server. So it says, okay, I'm this microservice. Here I am. I'm on this IP address and node. Now, the Zool proxy is also in communication with the Eureka server. When your request comes in through the gateway, and it knows to route to that node of that microservice. Now that microservice can go down, that box that's running on could get terminated, and you could bring up another microservice on another box, and the process would go through the same, where now it's registered again with the Eureka server, gets this configuration. So obviously you're going to be running multiple nodes of those microservices. So now anytime those microservices can fail, a node could fail, and the system is now self-healing because now you have that redundancy there. And it's also very scalable this way. So as different services become hotspots, you can spool up additional nodes. And what's important in a distributed architecture like this is that it is elastic. You see the Logstash and Kibana. This is quite a bit different from having a big monolithic application where you have one spot to go look at the logs on. Now you could have dozens, if not hundreds, of nodes out there, each collecting logs. That's why you use something like Kibana and Logstash. So this is a distributed architecture. You can see that what I have here is much more broad in terms of entire system architecture. And the purpose of this course is to look more granular at Spring 5 and what's going on inside of Spring Framework 5. Now, reactive programming is very important and is a useful implementation technique. So now we're going from the overall system architecture with reactive systems down to reactive programming, which is like the individual nodes in a microservice. So one is broad and one is very granular. Reactive programming focuses on non-blocking asynchronous execution, and this is a very important characteristic of overall reactive systems. But at the end of the day, reactive programming is just one tool in building reactive systems. So I think it's a goal. We all want to have very fast, very reliable systems. So it's important to understand the distinction here. So one is an overall architecture, but we're going to be diving into reactive programming, which is an implementation technique of a very granular service. All right, what is reactive programming? So this is kind of a rather meaty topic today. So the big thing about reactive programming is going to be focusing on processing asynchronous streams of data. So we'll take in a stream of data and process it in an asynchronous way. A good quote here by Gerard Barry, French computer science guy. Reactive programs also maintain a continuous interaction with their environment, but at a speed which is determined by the environment, not the program itself. Reactive programs work at their own pace, mostly deal with communication, while reactive programs only work in response to external demands and mostly deal with accurate interrupt handling. Real-time programs are usually reactive. So that's a fairly comprehensive statement there about reactive programming. But the big thing is that you want to remember that you're processing mainly events. It's going to be some type of event or a stream of events is what you're going to be working with in a reactive programming context. So a lot of common use cases for reactive programming are external service calls where you're calling out to somebody else, or highly concurrent message consumer. Actually, that they're starting to do batch processing with reactive programming, where you have a batch of data that you need to process. And in the old day, you'd put it on this big server and just let it crank away. Now we're actually going into a streaming mentality and getting some nice efficiencies out of that. And one of it the goals of some of the frameworks is to provide an abstraction over it being asynchronous. So, meaning that you, as the developer, when you're working with these frameworks, you're not really totally aware that it is an asynchronous or synchronous application that you're working with. So, it's easy to forget that's actually happening under the covers. So, some core features of reactive programming, we already talked about data streams and being asynchronous. Another one is non blocking. Then we also have back pressure and failures as messages, or some people call it failures as first class citizens. And we'll get into each one of these coming up. So, data streams, that's kind of a nebulous term. It can be just about anything. It can be like mouse clicks, mouse movements, or other user interactions. So this is pretty common and when you're working with GUI applications. But it can also be like JMS messages, sending and receiving REST service calls, monitoring a Twitter feed, stock trades, processing a list of data out of a database. So a stream is just a sequence of events ordered in time. And these are events that you want to be listening to and taking some type of actions. So asynchronous, the events are captured asynchronously. A function is defined to execute when the event is emitted. There's a different function that you can use when an error is emitted. And then finally, there's a function that's defined when the complete event is emitted. So you might have just like one item on your air quotes data stream, or you could have 5 items and then you get a done signal. So these are all different functions, and we'll see these coming in. I'm just laying down some concepts here right now. An important piece of the picture is the Gang of Four observer pattern. So this is an iconic book, Gang of Four. This is the observer pattern out of here. And basically you have a subject, and the processing that we're going to be seeing with reactive programming kind of is founded on this, not exactly, but fairly close to this. So you'll have a subject and then you'll have an observer, and that observer is going to take some type of action. So the subject is going to change and then it will notify the observers. So when the subject changes, the observers get notified. So Reactive X extended it, and they actually have a slogan saying that it's observable done right. So this is timeline. You can see in the top left corner there, they're talking about a timeline, and those are events that have been emitted by the observable, and these can be different things. And then they take some type of action, and here we're calling it a flip. So we're doing some type of flip action, and you can see through time you have the stream of events, and you get a result on the other side of it. And then in the bottom right there, we also have an event if for some reason that observable terminates abnormally. Now in that center box there, that transformation, there's a lot that can be happening with that. You can subscribe to certain events. You can say I want like every third event. You can put a filter on there before it gets down to the bottom and the action is taken. So this has a lot to do with the Java 8 Streams API, where you have a lot of interaction of controlling what the events are going through that. Non-blocking is another key concept. This is pretty complex, but the basic concept is in blocking code, the code is going to stop and wait for more data. So it could be reading from a disk and you're going to wait for the disk to set up. Non-blocking, in contrast, it's going to process what's available and then ask the sender to be notified when more is available. So, but the core concept here is when you're non-blocking, that task or that thread is going to go on to something else. Where in blocking, you're going to stop and block and wait. Now, here's an example of a typical multi-threaded server. So we have requests coming in, and they're going to get blocked at certain points. And they'll block and wait. And traditionally in the Java community, we're thinking, okay, we have lots of cores, lots of threads that we can use this, and it's actually a good thing. So we can have a thread wait while the IO catches up and do something else with the other threads on the server. So it's fairly efficient. It does scale pretty well, and this is at a very, very low level. And this has been tradition for a long time. And then what happened was really what grabbed the community's attention is Node.js came out, and they don't have much control over threads. So they set up a event loop, and in Node.js, if you block, you really kill the system performance. So what happens is there's a an event loop, and they have a very small thread pool, but they do all non-blocking. So what happens is nothing waits. It processes it right through, and there's no threads waiting. And they do put up a lot of impressive numbers in terms of performance. I think that's when the Java community really started going, hey, what's this non-blocking stuff? Kind of makes sense to get into. So the way I kind of envision my head is you can move a lot of traffic on a road like this, but it's all stop and go. So you're going to be stop and go, stop and go, stop and go. But in a non-blocking environment, you have a very efficient, speedy superhighway where everything's moving along efficiently. So let's take a look at this in a more typical context. So this is a web request. So we get a request that comes in on the port. Let's say we're posting JSON in a web service. We're going to parse that JSON probably with Jackson, and then go through some business logic, and ultimately we'll probably make the call to the database. The database is going to process it, and then it's going to return back. We'll parse it back to JSON and then return it on that port. Now, what's important to understand, I put red X's here, and in a traditional sense, each one of these is where blocking is going to occur. In the traditional servlet API, we have blocking in that. Traditionally in Jackson Parser, there's blocking in that. Calling the database, there's blocking in that. So these are all instances of where blocking occurs. In a reactive system, what's going to happen is that request is going to come in like a callable future, and it will get passed along until the last very minute, probably about where we're calling the database here. And then we are going to process that stream, parse the JSON, call the database in a reactive format. So that thread of processing will stay on the CPU longer in one continuous chunk. It's not going to block, stop, wait, and then come back. So the CPU is able to handle that more efficiently because it's sitting there in the same context, and it's not stopping and waiting and stopping and waiting, stopping and waiting. Next up is back pressure. So this is an important concept. The subscriber is able to throttle data so that you can set up, say, give me 100 records, or give me 10 records, or give me 1,000 records at a time, or elements. So this is an important concept to allow communication between the subscriber and publisher. And I put a little fire hose here. So basically, in a reactive architecture, you want a way to throttle things. If the client is becoming overwhelmed, you want to be able to back it down. So in the States, we have a saying about trying to drink from a fire hose. Obviously, you don't want to be drinking from a fire hose. That would be a bad idea. Okay, the next up is failures as messages. And exceptions are not going to be thrown in a traditional sense. So if we're processing a stream of data and we have some type of function there, if we threw an exception, it would break the processing of the stream of data. Instead, we are going to gracefully handle the exceptions through a handler function. So we called out that before. So this is a core concept that we don't throw exceptions, but we do handle them gracefully with a specific handler function for when things do go wrong. Now, a couple key takeaways that I want you to have from this presentation is reactive programming is going to focusing on processing streams of data. And it's not for everything. So traditional CRUD applications are still alive and well. There's times where you just want to be processing a form post, and that's perfectly fine. So it's going to be very application specific. You can do it. I expect to see the community is probably going to start overusing it. But the traditional CRUD applications, what we've been doing as Java developers, still going to work just fine. As far as performance goes, you can expect the system is probably going to gain some advantages, but this area is still very early and still evolving. So yeah, you do expect to see performance gains in terms of server efficiency, but like everything else in terms of performance, your mileage is going to vary. All right, in this video, we are going to be talking about reactive streams and how they relate to Spring Framework 5. Now, the Reactive Streams API, the goal was to create a standard for asynchronous stream processing with non-blocking back pressure, so all the reactive stuff that we've been talking about. The initiative was started in 2013 by engineers from Netflix, Pivotal, and Lightben, and Lightben is formerly TypeSafe. And just as an interesting tidbit, Rod Johnson, the founder of Spring Framework, actually worked on the board of directors for TypeSafe. I think at this point in time he's moved on. I'm not 100% sure on that. but I think he is pursuing other things at this point in time. But he was with TypeSafe, and Lightbend is now the company that has been VC funded, and they are supporting the Scala language, and Scala is some cool stuff. And then the Reactive Streams API is actually just a set of 4 interfaces which define the API, and then there's actually a specification about the behavior we expect in the implementation of those interfaces, but I'm not going to get into that. The 1.0 release was done in 2015, and what's notable is under JEP 266, Reactive Streams is now going to be part of the Java 9 JDK. So that will be a fully recognized feature inside of Java 9. And so that is going to be there in the future. Now, there's a number of adoptions, and the landscape right now is changing quickly because there's always new stuff coming out, and the Reactive community is becoming more and more active. So we have a CosStreams, and that's Scala, MongoDB, Ratpack, Reactive Rabbit, which I have not played with yet, but I hope to. Project Reactor, that's the Spring implementation. RxJava, if I remember right, that is from the folks at Netflix. So, and all these support the Reactive Streams API. So these different adaptions should, at least in theory, play nicely together and work nicely together. Now, like I said a moment ago, the 1.00 release was done in 2015, and I am recording this in August 15th, 2017. So just not even the following week that the 1.0.1 release was done. Now, that release, it's a minor release, and the API, the interface classes, did not change at all. It was more of a specification change of how they behave. I think they clarified some things in there, but the interfaces have remained the same. So let's take a quick look at some of the interfaces. We have a publisher, and this is going to provide a unbounded number of elements. So that's our data stream. And then we have a subscriber. So this is going to consume from a publisher, obviously. Subscription, you can see that these interfaces are pretty simple to use, and a lot of times our abstraction is going to be really, really simple to use, and we'll be definitely looking at examples of these. And then finally, processor. To give you an idea how these all fit together, this is how the streams are processing. So a publisher is going to be publishing events which are going to get consumed by a subscriber, and a subscriber is going to have a subscription to a publisher. And through that subscription, the subscriber can give feedback on demand or back pressure. So I hope you can start envisioning how this works. So we're going to be definitely be looking at some live examples and the coding of this. But this is how these interfaces fit together. Now, in Spring MVC and Spring WebFlux, the reactive stuff is going to be under the right-hand side, the Spring WebFlux. And what has happened inside the Spring framework is the servlet container, the servlet API, is not reactive. It is blocking. So Spring Framework guys created a whole new stack, a whole new web framework inside of Spring called Spring WebFlux. Now, top of these, we're still going to be using the controller and request mapping annotations, or a whole new functional API called router functions. You can use either one of these with Spring Web MVC or Spring WebFlux. So this is all handled by the framework. You can use either stack, whether you want to be reactive or use traditional servlet. And there's really nothing wrong with traditional servlet. It still works. I mean, it's still a very robust programming API that we have to deal with the web environment. So it's still inside the Spring framework. It's not mandatory to use. It's not bad to use. But for the reactive functionality, when you're in these high volume streaming environments, we do have this whole new reactive framework with Spring WebFlux, and we'll be looking at that a lot closer. Now, the Spring Web MVC stuff does still support the traditional servlet container, but the WebFlux, we now have the option of Tomcat, Jetty, Netty, or Undertow, and these are different reactive implementations that we can work with. Netty is probably the most robust option, but Tomcat is a little bit simpler and widely used. So your implementation to your needs can vary, but you do have options there, and the Spring framework will work with any of those. Now, the next thing we need to talk about inside the Spring framework is the Spring reactive types. So there's two new reactive types introduced with Spring Framework 5. Mono is a publisher with 0 or 1 elements in the data stream. And this is important to understand, 0 or 1. And then Flux is 0 or many elements inside the data stream. And I want to point out that both of these types implement the Reactive Streams Publisher interface. And I expect that you can probably work with just about any publisher inside of the Spring Framework web APIs, but we are going to be focusing on using the Mono and Fluxes and using these data types and setting up our Spring controllers now. And what you're going to see going forward in the class is, because of the way Spring, let me back up one slide, because of the way Spring set up things, our controller and request mapping still there. We still set up our controllers the same way, but now we are going to be working with these return types. If we have a reactive data store like we do with Mongo, that reactive call will go through full stack, and that is our goal to get here. But we need to define this terminology first. In the next upcoming videos, we're going to be looking at examples of converting over the controllers that we've been working with to start leveraging these reactive types. All right, we've been going through a lot of PowerPoint slides in this section of the course. Kind of apologize for that. I find the slide decks get a little boring after a while, but we had to cover a lot of content, getting our heads around this reactive programming stuff. So we've laid down a lot of groundwork here. But now I want to jump over to IntelliJ, and we're going to look at some hands-on examples. This is really just to get our feet wet with reactive programming. So we're going to look at the reactive types within the Spring Framework, the monos and the fluxes. And what I have is a pretty simple little project, a couple data types, and we're going to go in and play around with those. Now, I will check all this into GitHub. It's in a little sandbox of collection of stuff that I have. Go ahead, check it out, take a look. I encourage you to play with it, start getting used to working with these reactive objects. This is an extension of the Java 8 streams. So I'm not covering all that technology. I'm not going to cover it in detail, but we are going to be utilizing it a lot going forward. So the reactive types in the Java 8 streams are very, very closely related, and you use a lot of the same techniques. But I think I got some fun examples here. And again, this is just to get our feet wet. We're going to go through and just start getting used to using these reactive types that are available in Spring Framework 5. All right, we've been talking a lot about reactive programming. Let's take an actual look at some examples. And what I have is a little project. I have a sandbox up on GitHub. I'll leave a link to the project here for sure. Once I get it checked in, you can see everything's green there in IntelliJ, meaning that it hasn't been committed and pushed, but I will definitely leave that in the course resources so you can see this example. And what I have is a pretty simple example. We've got two objects, just a person and a person command. So I just have first name, last name, and I got a little helper method here that we'll be using to get output. So we'll have the little Pojo here say its name. And of course, we're using Project Lombok. So we have data, no args constructor, all args constructor. And then I have a command here so to emulate a command object. And we'll use that for some type transformations. And I put a convenience method on there with the constructor to create a person command from a person object. So nothing too exciting there. Now let's take a look at the test. And I wrote everything in tests so we can go through a number of different examples here. And if you don't know, if you've taken my courses in the past, you know that I'm a Burn Notice fan. So we have the characters from Burn Notice here. Michael, Fiona, good old Sam, and Jesse. And let's take a look at some of the examples here. And the first one we're going to look at is just a mono test. And what this is doing here is we create a new person mono, and we do mono and just is going to create a mono object from the given object that you're working with. So this gets us a person mono, and if we want to get the person object out of the mono, we call the block method on it, and that's going to return back that person. And now we can do a login. I'll go ahead and run this little test here so you can see the output of the example. And we can see there that we did get Michael Weston back from that test. Now let's go ahead and take a look at the next test here. And in this case here, we're going to use the map function to return back that person. So actually, I'm going to reformat that a little bit. So Now that's a little bit better formatting. And in this case, map is a transformation object, just like Java streams. The Spring Reactive stuff has that map function. So we're going to do a type transformation in that example. And again, we're just going to do say name. And we'll go ahead and run this. And we should see Fiona in the output. And again, you need to remember that we are calling this block function here, and that's what triggers it, because really this is essentially a future, and it won't execute until something blocks on it. Now, next up here, let's take a look at a filter example. And bring that up to the top of the screen. And in this case, what we're going to do is filter out that mono. So we're going to do a stream. So we'll get a stream on that. And we're going to say, hey, I'm asking for foo. And we're going to take the SAM object. And when I run this, we'll get a null pointer exception, because I'm going to filter that and no results are going to be back. So that person is going to be a null object, or null. So in this case, this guy is going to toss a null pointer exception, and which it does. And in JUnit here on line 47, we're saying I expect a null pointer to come back. In all these examples so far, we've been looking at mono. So let's take a look at a flux. And remember, a flux is multiple objects. So a mono, just to reiterate, a mono is 0 or 1, where a flux is 0 or many. So in this case here, let's go ahead and run the flux test. We'll see that he runs pretty quick. And again, just like mono, we are using a flux, and it can take in multiple properties. So a couple different ways of creating the fluxes. But here you can see that we did get the flux, and when we subscribed on it, we are passing in the log info, and we are getting our log output here from the flux objects. So collapse this guy, and let's take a look at the next one. Now here we can also test a filter, which I did not. And he pauses. Okay, I realized I forgot to put in a filter option on this, and so I went in and did that real quick. And what we're going to do is filter on persons, basically for Fiona. Let's go ahead and run this now, make sure that works. And we can see that we only get Fiona. So we still had, just like on the example before, we still have the 4 objects in there. So we still have the 4 objects going into the flux. But now we are doing a filter operation on it, and we are going to filter out just where Fiona is. And now here, we can also do this, and we're doing a delay. So we're going to emit every second here. And this is a little surprising if you're not used to streaming. See how everything just went by? And what happened there is that we're delaying, but because it's running in the background, we didn't wait for that output. So it ran, and the test terminated before that duration expired. And a way around that when we're testing, I want to show you this here, is to use a countdown latch. And what we can do here is we're still going to do a delay of 1 second, but now on complete of that stream, we are going to count down that latch. And this here on line 100 tells the test to wait until the countdown is complete. So a handy way to do that. And now if we run this, you can see that it's going to go through it, and now we're going to get the output every second. And then the one last test that I want to show you is we are going to add in a filter. So let's go ahead and run this guy. And in this case, we'll just get Michael and Fiona, because the others did not qualify. So we're looking for a first name that contains I, and you can see up here, scroll all the way up, Michael and Fiona are the only ones. Sam and Jesse do not match that criteria. So a number of different things that we can do with the flux and the monos, the reactive types. It's a lot of fun. It's a little bit different. It takes a little bit of getting your head around it, but I wanted to record this video and just show you some examples of these in action, and I hope you found this video helpful. All right, this concludes the section of the course introducing you to reactive programming. Now, I'm sorry, I hope this wasn't too boring. We didn't have a lot of hands-on coding example, but really we need to transfer a lot of information about reactive programming and just trying to lay down a foundation of the concepts and stuff that we have to deal with going forward. So it takes a lot of getting around your head around it. It is definitely a different programming paradigm. It's going to feel pretty clunky at first when you're working with it. But remember, reactive is all about dealing with streams of data. So streams are going to be coming through these libraries. So it's really quite a different programming paradigm because you're dealing with basically a future object that you're passing, and then something is going to ask for that data, and then it's going to trigger all that logic into your code all at once. So it does take some getting used to for sure. But coming up, we are going to be looking at some more concrete examples, and we'll be stepping through it slowly and getting you more and more acclimated to reactive programming with the Spring framework.